calculate the feeder ampacity when the largest motor is part of a group of motors, such as in heaters, you only apply the 125% multiplier from NEC 430.24 into the single largest motor. It is essential to identify which motor is the largest within the entire load. Do not apply the 125% multiplier to the ampacity of all motors, just the largest one. Consider a scenario with 3 heaters where one heater has a motor that is larger than the other 2. The calculation for the feeder ampacity would include 1.25 times the ampacity of this largest heater motor, plus the other loads. For example, the calculation would be the feeder ampacity equals 1.25 times the largest heater motor ampacity, plus 125% times the lighting load, plus 100% times other non-motor continuous loads, plus 125% times any other motor loads, like a roll-up door motor ampacity. This approach ensures compliance with the NEC while accurately accounting for motor loads. Understanding how to handle HVAC loads and feeder calculations is similar. If the HVAC manufacturer provides a minimum circuit ampacity, or McCaw value, it is generally assumed that the 125% multiplier for the largest motor has already been factored into that MCA value. In this case, include the MCA value directly in your feeder ampacity calculation. This simplifies the process, as you do not need to calculate the motor ampacity separately. The feeder ampacity calculation would simply include the MCA value of the HVAC unit. However, if the manufacturer does not provide an MCA value, you must determine the ampacity of the largest motor within the HVAC system using the appropriate NEC tables. Once you have determined the ampacity, apply the 125% multiplier to it and include this value in your feeder ampacity calculation. The calculation would be feeder ampacity equals 1.25 times the largest HVAC motor ampacity plus 125% times the lighting load, plus 100% times other non-motor continuous loads, plus 125% times the roll-up door motor ampacity or any other motors. By following these steps, you ensure that the feeder ampacity is adequately sized to handle all connected loads, including the largest motor, while adhering to NEC guidelines. Now let's delve into some specific examples to solidify the understanding. Imagine an electrical panel that feeds several loads, including welding receptacles, heaters, lights, a roll-up door, a lube shop, and a single-phase panel. The voltage is 480/277 volts. The lighting load is continuous, requiring a 125% multiplier as per NEC regulations. The heaters also require a 125% multiplier according to NEC 430.24. The question arises how to handle the largest motor, especially if it is within the heater load, using NEC 430.24. The correct approach is to identify the single largest motor, regardless of whether it is part of the heater load. Only the ampacity of that specific motor is multiplied by 1.25. Let's say the heater with the largest motor has a 50 kilowatt motor. You do not apply 1.25 to all 3 heaters totaling 187,500 watts. Instead, you find the ampacity of the largest individual motor from the NEC tables, multiply that ampacity by 1.25, and include that result in your feeder calculation. For instance, if the largest motor's ampacity is 100 amps, you would add 125 amps to the feeder calculation, along with the other loads calculated appropriately. This method prevents oversizing the feeder while ensuring it can handle the necessary load. The side question addresses a similar scenario but focuses on HVAC systems. HVAC units often have multiple motors, and their load calculation can be confusing. If the manufacturer provides an MCA value, it simplifies the process considerably. The MCA value already includes the 125% multiplier for the largest motor within the HVAC unit, so you can directly use the MCA value in your feeder calculation. You do not need to separately calculate the largest motor's ampacity or apply the 125% multiplier. However, If the manufacturer does not provide an NCA value, you must determine the ampacity of the largest motor within the HVAC system using NEC tables. Then, you apply the 125% multiplier to that ampacity and include the result in your feeder calculation. For example, if the largest motor within the HVAC system has an ampacity of 50 amps, you would add 62.5 amps, which is 1.25 times 50 amps, to the feeder calculation. To summarize, firstly, identify the single largest motor among all the loads connected to the feeder. Secondly, if an NCA value is provided by the manufacturer for equipment like HVAC units, use that value directly in the feeder calculation. Thirdly, if an NCA value is not provided, determine the ampacity of the largest motor using NEC tables. Fourthly, apply the 125% multiplier to the ampacity of the largest motor. Fifthly, include the result in the feeder calculation along with all other applicable loads, such as lighting, receptacles, and other motors. This ensures that the feeder is appropriately sized and complies with NEC requirements. Let's elaborate on determining the ampacity of a motor from NEC tables. The NEC provides tables that list the full load current or flow of motors based on their horsepower, voltage, and phase. These tables are essential for calculating the required ampacity for feeder and branch circuit conductors. Firstly, locate the correct table for the motor's voltage and phase. For instance, if you have a 480 volt, 3-phase motor, you would use the table specifically for 3-phase, 480 volt motors. Secondly, find the motor's horsepower rating in the table. The table typically lists horsepower values in increments. Thirdly, read across the table to find the corresponding full load current or a flow for that motor. This FLA value is the ampacity you will use in your calculations. It is important to note that the FLA value from the NEC table is used for calculating conductor sizes, overcurrent protection, and other aspects of the electrical system. Do not use the motor's nameplate current rating for these calculations unless the nameplate value is higher than the table value. In cases where the motor is marked with a service factor higher than 1.15 or a temperature rise higher than 40 degrees Celsius, you may need to adjust the FLA value according to NEC guidelines. In addition to the motor's FLA, you must also consider other factors such as the motor's starting current and duty cycle. The starting current, or inrush current, can be significantly higher than the FLA and must be accounted for when selecting overcurrent protection devices. The duty cycle refers to how frequently the motor starts and stops, and how long it runs continuously. For motors with intermittent duty cycles, you may be able to reduce the conductor size and overcurrent protection based on NEC guidelines. Now consider a scenario where you have multiple motors connected to a single feeder, and you need to determine the overall feeder ampacity. Firstly, identify the largest motor and determine its FLA from the NEC tables. Secondly, multiply the FLA of the largest motor by 1.25 as per NEC 430.24. Thirdly, determine the FLA of all other motors connected to the feeder. Fourthly, add the 1.25 times the FLA of the largest motor to the sum of the FLA of all other motors. Fifthly, add any other continuous loads, such as lighting or heating, multiplied by 1.25 if they are considered continuous loads as defined by the NEC. Sixthly, add any non-continuous loads at 100% of their value. The result is the minimum required ampacity for the feeder. It is important to select conductors with an ampacity equal to or greater than this calculated value. In some cases, you may need to upsize the conductors to account for voltage drop or other factors. Voltage drop can be a significant issue in long feeders, as it can reduce the voltage available at the motor terminals and affect motor performance. The NEC provides guidelines for calculating voltage drop and recommends limiting voltage drop to a maximum of 5% from the source to the farthest motor. To minimize voltage drop, you can increase the conductor size, use conductors with lower resistance, or reduce the feeder length. Another consideration is the type of overcurrent protection used for the feeder. The NEC allows for various types of overcurrent protection, including fuses and circuit breakers. The selection of overcurrent protection depends on the motor's characteristics, the feeder's ampacity, and other factors. It is important to coordinate the overcurrent protection with the motor's thermal overload protection to prevent nuisance tripping and ensure that the motor is adequately protected against overloads and short circuits. Thermal overload protection is typically provided by overload relays, which are installed in the motor starter. These relays sense the motor's current and trip the circuit if the current exceeds a predetermined value for a certain period of time. The overload relay setting should be carefully selected to match the motor's full load current and service factor. In addition to the feeder ampacity and overcurrent protection, you must also consider the grounding requirements for the motor and feeder. The NEC requires that all electrical equipment be properly grounded to provide a low impedance path for fault current and to protect against electric shock hazards. The grounding system typically consists of a grounding electrode conductor, a grounding electrode, and equipment grounding conductors. The grounding electrode conductor connects the neutral point of the electrical system to the grounding electrode, which is typically a ground rod or a metallic water pipe. The equipment grounding conductors connect the metal enclosures of electrical equipment, such as motors and panels, to the grounding system. This ensures that any fault current will flow back to the source and trip the overcurrent protection device, energizing the circuit and preventing electric shock. Furthermore, it is also crucial to consider the ambient temperature when determining conductor ampacity. The ampacity of conductors is typically rated at a specific ambient temperature, such as 30 degrees Celsius. If the ambient temperature is higher than this value, the conductor ampacity must be derated according to NEC tables. This derating is necessary because the conductor's insulation can degrade at higher temperatures, reducing its ability to carry current safely. The NEC provides tables that list the derating factors for various conductor types and ambient temperatures. To apply the derating factors, multiply the conductor's ampacity by the appropriate derating factor. The result is the adjusted ampacity, which must be equal to or greater than the calculated feeder ampacity. Additionally, it's necessary to account for conduit fill when running multiple conductors in a single conduit. The NEC limits the number of conductors that can be installed in a conduit to prevent overheating and insulation damage. The allowable conduit fill depends on the type of conduit, the size of the conductors, and the number of conductors. The NEC provides tables that list the allowable conduit fill for various conduit types and conductor sizes. If the conduit fill exceeds the allowable limit, you must increase the conduit size or reduce the number of conductors. Proper conduit fill is essential for ensuring the safe and reliable operation of the electrical system. In summary, accurately calculating feeder ampacity for motor loads requires a thorough understanding of the NEC, including the rules for motor ampacity, overcurrent protection, grounding, and ambient temperature derating. By following these guidelines, you can ensure that the electrical system is safe, reliable, and compliant with all applicable codes and standards. This comprehensive approach involves firstly, accurately identifying the largest motor connected to the feeder. Secondly, correctly applying the 125% multiplier to the ampacity of that largest motor. Thirdly, properly accounting for other continuous and non-continuous loads. Fourthly, carefully considering ambient temperature and conduit fill. Fifthly, coordinating overcurrent protection with motor overload protection. By paying close attention to these details, electrical professionals can design and install electrical systems that meet the needs of their clients while ensuring the safety of people and property. Remember to always consult the latest edition of the NEC and any applicable local codes and regulations before performing any electrical work. Furthermore, it's important to emphasize the significance of regular maintenance and inspection of electrical systems. Over time, electrical components can degrade due to heat, moisture, vibration, and other factors. Regular maintenance, such as tightening connections, cleaning equipment, and testing components, can help to prevent failures and extend the life of the electrical system. Inspections should be performed by qualified electrical professionals who can identify potential problems and recommend corrective actions. A comprehensive inspection program should include visual inspections, infrared scanning, and electrical testing. Visual inspections can identify obvious problems such as loose connections, damaged insulation, and corroded components. Infrared scanning can detect hot spots that may indicate overloaded or failing component. Electrical testing can verify the performance of the electrical system and identify any hidden problems. By implementing a proactive maintenance and inspection program, you can minimize the risk of electrical failures, reduce downtime, and improve the overall safety and reliability of the electrical system. In addition to regular maintenance and inspection, it's also important to keep accurate records of all electrical work performed. These records should include detailed information about the design, installation, testing, and maintenance of the electrical system. Accurate records can be invaluable for troubleshooting problems, planning future upgrades, and complying with regulatory requirements. The records should be stored in a safe and accessible location and should be updated whenever any changes are made to the electrical system. By maintaining accurate records, you can ensure that the electrical system is properly documented and that future work can be performed safely and efficiently. Moreover, ongoing training and education are crucial for electrical professionals to stay up to date with the latest technologies, codes, and best practices. The electrical industry is constantly evolving, with new products, new techniques, and new regulations being introduced all the time. Electrical professionals must stay informed about these changes to provide the highest quality service to their clients. There are many opportunities for ongoing training and education, including seminars, workshops, online courses, and industry conferences. By investing in ongoing training and education, electrical professionals can enhance their skills, expand their knowledge, and improve their career prospects. Furthermore, adherence to safety protocols and the use of appropriate personal protective equipment, or PPE, are non-negotiable aspects of electrical work. The electrical work can be dangerous, and it is essential to take all necessary precautions to protect oneself from injury. Safety protocols should be followed at all times, and appropriate PPE should be used for every task. PPE may include items such as safety glasses, gloves, hearing protection, and arc flash suits. Before starting any electrical work, it is important to assess the hazards and select the appropriate PPE. It is also important to ensure that all PPE is in good condition and properly maintained. By following safety protocols and using appropriate PPE, electrical professionals can minimize the risk of injury and ensure a safe working environment. Ultimately, understanding and applying the NEC guidelines for motor feeder calculations is a critical skill for electrical professionals. This knowledge ensures safe and efficient electrical installations, preventing overloads and potential hazards. Remember to prioritize safety, stay updated with code changes, and consult with experienced professionals when necessary.